So welcome back. This is the second talk of the day. Our second speaker is Professor Noah Friedkin. Noah is a professor in the Department of Sociology at the University of California, Santa Barbara, and he is a AAS fellow and editor-in-chief of the journal Mathematical Sociology. His research interests are in network science modeling of interpersonal inference systems. This is also is the topic of his today's talk. So he has published 2 award-winning books on this subject along with numerous journal publications in which modeling predictions are evaluated with data collected from experiments on human subjects. During the past 6 years, his work has been conducted with people from control theory and computer science. Actually, I want to mention Noah don't really need my introduction. If you have been following the talks in this workshop, his name has been mentioned again and again. The model, Friedkin and Johnson model, named after him, is one of the most influential model in opinion dynamics. Today, he's going to talk about interpersonal inference systems, constructions, mechanisms, applications, and experiments. So from the title, you can see there's lots of things we are looking for. With that, Noah, please take it away from here.
Okay, thank you. Okay, so it's a bit awkward to find myself located between talks on bots and misinformation. So let me travel back in time and pretend that I'm the 4th talk on in the session on opinion dynamics. My talk is organized as follows. I'll describe the model that has been the focus of my research over the past 30 years. This 30-year engagement may appear obsessive, but its motivation was my belief that a single model could be developed that would allow an integration of various seemingly disparate lines of inquiry in experimental social psychology. I would have dropped the model had this belief been eroded. Then I will describe work conducted during the past 5 or 6 years that has extended the applications of the model and gone deeper into tests of its mechanistic predictions. My collaborators in this work are Francesco Bullo, Roberto Tempo, Anton Prushnikov, and Ambuj Singh. Francesco introduced me to Roberto Tempo introduced me to Anton, and I met Ambuj Singh on the squash court where I never won a game with him. Let me make a further remark on Roberto. Never forget Roberto's visit to UCSB, in which we spent an entire beautiful morning tossing ideas across a table outside a cafe. I miss him greatly, as I'm sure many of us do. This influence system is a generalization of the seminal French Harari de Groot system, in which the AII construct permits an ongoing level of attachment to an individual's initial displayed position on an issue. The scalar equation is an information integration mechanism that automatically generates an issue-specific influence network. The network is assembled by the group members' accorded weights to other group members in response to their displayed positions on an issue. In other words, it's a cognitive network that is the consequential byproduct of the individual's information integration mechanism. The fundamental open problem in this framework is whether the postulated convex combination information integration mechanism is an embedded operation of the human brain. Its influence centrality measure is given by the evolving VK matrix, which appears in the matrix equation of the system. The equilibrium Vij values gives the total direct and indirect influence of J's initial position on I's equilibrium position on an issue. Applications and validations of the model in human subject experiments minimally require measures of group members' initial pre-discussion and post-discussion positions on an issue, and a measure of their WIJ accorded relative weights to themselves and other group members. The measure of AII may be specified as a function of WII, for example, AII equals 1 minus WII, or solved from the scalar equilibrium equations of the system. Let me introduce you to this the notion of a choice dilemma, and the literature out of which this set of experiments grew. Stoner's MIT MA thesis reported risky shifts on choice dilemmas, and this I'll define and this triggered this finding. It was never published, but this MA thesis triggered a lot of work in social psychology, particularly among social psychologists located in departments of psychology. So there's this classic line of work on risky shifts that developed, and basically the idea behind these, what Stoner reported, okay, the design of the experiments that Stoner conducted is as follows. So let me get you a fix on that. So groups were assembled, and a choice dilemma, a sequence of choice dilemmas were posed to them, on which they reported their initial positions. The group opened then open discussion on the issue, and then at the close of the session, they reported their final positions on this choice dilemma, on these choice dilemmas. Now, what is an example of a choice dilemma? Consider a surgery issue. So you're told that you have to, that you require surgery to correct a heart problem. And you have an option. If you agree to the surgery, there's a probability that you're going to die. On the other hand, if the surgery is successful, you can return to the lifestyle that you enjoyed without any constraints. And so then the question is, what's the probability of a successful surgery that you require to make the decision to get the surgery? And individuals vary dramatically in their positions on this. So questions like this, a whole sequence of questions on this, were posed to each group. And what Stoner found was that there was a risky shift. And this risky shift was measured as the difference. The group has a mean initial opinion on this issue, on this issue. After they discussed it, Stoner found that they shifted to they were more risk tolerant. So they tended to be, that's why it's called a risky shift. So this opened up a vigorous line in social psychology, dozens and dozens of studies. And as it turned out, the risky shift hypothesis was dismantled. I mean, there's no strong evidence for it. So this was replaced with another hypothesis, which is called the group polarization hypothesis. And that hypothesis says that if the group mean on a scale, imagine a scale in which there's a neutral value and above which you accept greater risk on this scale, below which you accept you're less risk tolerant. So the group polarization hypothesis says that if the mean initial opinion on this issue is above this neutral point, then the group discussion will tend to elevate toward greater risk the mean final opinion on this issue. But if the mean initial position on this issue is below this neutral point, the group discussion operates to move further towards risk intolerance. So this hypothesis was pursued vigorously in dozens and dozens of studies. And the researchers that were focused on this line of research broke into camps, disputing camps on the mechanism and theory about why this phenomenon seems to appear in the data, in their data. And that dispute was never resolved. Now, the thing that you need to realize about this is that this is basically an input-output kind of model in which there's a black box. And the black box consisted of, what exactly was going on in the group that generated individuals, the group members' movements towards greater risk accepted or less risk acceptance. And that was what the sort of conflict in this among the investigators in this field was all about. But they never specified they never specified the interpersonal influence system that was occurring in the group. Well, this hypothesis over time also was discarded. And the final conclusion, there was no settlement on this. And they finally concluded that the only thing that they could rely upon, the only reliable finding out of this literature was that there was a choice shift. In other words, that there was a difference between the mean initial opinion of a group on the issue and their mean final opinion, right? And with no account of what kind of choice shift that was, right? Toward greater risk acceptance or less tolerance of risk. So early on in my work on this, I thought, well, let's specify the influence system. And so I set up the model that I showed you, and conducted an experiment that had, the report of initial opinions on each issue, a report of their final opinions, along with measures that allowed me to specify this influence, the weights, the accorded weights for the influence network. That was published decades and decades ago. And the finding of that was that it's, these groups are highly it's not surprising, the groups are highly idiosyncratic, and depending on how stubborn people are, how open to influence they are, dependent on the network topology, you could get all sorts of different movements. I mean, there was just a broad domain of idiosyncratic, group idiosyncratic conclusions on specific issues. But the important point was the influence system provided remarkably accurate predictions of where the individuals the equilibrium, the settled positions of the individuals were in this setting. This article reports advancements in the influence system evolution in small deliberative groups and a set of empirical findings on such groups. The theory elaborates the specification of single issue opinion dynamics of such groups, which has been the focus of theory development in the field, to include group dynamics that occur along the sequence of issues. In the classic tradition, the set of data that is obtained on the set of issues that each group took were simply pooled. But this article says that there is deals with the possibility that there are dynamics that occur, that evolve across a group's sequence of influence, across the sequence of issues, right? Across the sequence of issues or along the sequence of issues. The theory predicts an evolution of influence centrality along sequences of issues based on an elementary reflected appraisal mechanism that modifies the influence network structure and flows of influence in the group. Now, what is a reflected appraisal mechanism? This is a classic hypothesis in social psychology. The basic idea is that individual self-esteem, for example, are a function of the attitudes, the esteem in which other individuals hold that individual. So if other individuals have low esteem for a particular individual, this hypothesis says that the individual's self-esteem will be a reflected appraisal of the low esteem. So their esteem will be low. On the other hand, if the people that are the people who an individual is surrounded with hold that individual in high esteem, that individual's self-esteem will be high. So now consider a situation, which is the subject of this paper, in which imagine that you walk into a meeting and there's a discussion of an issue. Just think of committee meetings that you've sat in. And in this group discussion, you have had a large impact on the final position of the group. You have substantially determined the outcome of the group. Well, as you walk out of that room on that meeting, you're going to feel pretty good about yourself. And in the next meeting of that group, let's say it's a regularly scheduled committee meeting, you're going to walk into that group with a higher self-weight. If you've had walk out of that meeting and you've had no impact on the decision of the group, the next time that meeting occurs, you're going to walk into that with a lower self-weight. Now, this evolution of self-weights, so we postulate and find that group members' self-weights evolve in correspondence to their prior influence centralities along issue sequences toward a state in which one member controls the influence system. That's the basic finding. Now, it turns out that proving the convergence of this mechanism is a really difficult problem. We never solved it for the full model. We laid it out for several, we conveyed the problem to other colleagues. So can you figure out, can you figure out the conditions of convergence for this mechanism? And after they pondered on it, they couldn't arrive at it. So this is an open problem on this particular model. And The SciAm review paper that appeared on this was a simplified version of this that allowed proofs of convergence. But the general model, there has been no success in nailing down the convergence properties. All right. So how truth wins in groups is an important open problem. Classic experiments on groups dealing with truth statement issues present mixed findings on the conditions of truth abandonment and reaching a consensus on the truth. No theory has been developed and evaluated that might integrate these findings with a mathematical model of the interpersonal influence system that alters some or all of its members' positions on an issue. In this paper, we show that the model also applies to truth statement dynamics and substantially clarifies how truth wins in groups. Now, we dealt with the issues that we dealt with were analytical reliability problems. An example of such a problem is the following. Two medical teams are working independently to achieve a cure for a disease. The hope is that at least one of these teams will succeed. The success of research team A depends on the successful solution of two problems, A1, A2. The probabilities of their successful solutions are 0.6 and 0.45 respectively. The success of research team B depends on the successful solution of three problems, B1, B2, B3. The probabilities of their successful solutions are 0.8, 0.85, and 0.95 respectively. All of the above probabilities are independent. What is your estimate of the probability that at least one of these research teams will succeed in finding a cure? In this paper, we show optimal decisions on the distribution of finite resources are explicitly structured by mathematical models that specify relevant variables, constraints, and objectives. We report analysis and evidence that implicit mathematical structures are also involved in group decision-making on resource allocation distributions under conditions of uncertainty that disallow formal optimization. A group's array of initial resource distribution preferences automatically sets up a geometric decision space of alternative resource distributions. The group members have no idea they have set up such a space, and yet it is constraining. When a group's influence system generates a consensus on a suitable distribution, this distribution is a feasible point in the group's implicit decision space. So we report findings from 5 experiments on resource allocation issues within groups of human subjects. Experiment 1 is the classic problem of optimal allocation of funds to 3 categories of work on a device with an objective of maximizing the device performance. It's a simple problem that could be solved by hand. Experiment 2 relaxes the condition of a given objective function. With given constraints, the task is to attempt to reach consensus on a distribution that satisfies the constraints they have settled on. Experiment satisfies the constraints. Experiment 3 relaxes the condition of a given quantifiable objective and a given set of constraints. The task is now to reach a consensus on a set of constraints and then to reach a consensus on a distribution that satisfies all of the constraints. Then experiments 4 and 5 relax the condition of a given quantifiable objective and a set of given explicit constraints.
Hey, Noah, if I may interrupt. So I have a quick question. So can you comment more about this paper, or what kind of mathematical structures in these 5 different experiments?
Let's take the situation in which there are no pre-specified constraints. Those are experiments in experiments 4 and 5. So the individuals, they all set to have a set of initial positions, or let's say, in general, the set of initial positions on a multidimensional issue sets up a convex hull. And it sets up, and the nature of the influence system is this, that no opinions will be changed that are more extreme than the minimum and maximum displayed value on a particular dimension. And it turns out that that's very rarely violated. So the initial set of multidimensional positions sets up a space that is that has different contours depending on how you specify the problem. And the individuals, it's the feasible space, and they don't even know that it exists.
Interesting.
And yet they end up in somewhere in this space, either in a state of disagreement, or they fix on a position that's within it. It could be, right? So if you look at the paper we set up across the experiment, we set up different situations. Like if we had pre-specified constraints, that would automatically kind of create this hull, right? And so on. And we kept relaxing this, right? Kept relaxing the conditions on the constraints. So that's the implicit mathematical structure. It's a geometric structure, that the subjects are dealing with.
I see. Very interesting. Thanks. If you don't mind, can we also check whether there's some question from audience?
Okay.
If not, yeah, please go ahead. Yeah.
Okay, thank you. Okay, this is something that's in revise and resubmit. But I love it so much that I wanted to present it to you. So this deals with the topic of this group dynamics on multidimensional object threat appraisals. So the literature, this stems from a literature that was set up by Osgood et al., cross-cultural studies, in which they presented objects to individuals, and then the individuals were presented with a set of anonym pairs. So like good, bad, or strong, weak, or little, big. Just a whole eclectic array of anonym pairs that were scaled, right? And these in social psychology are called semantic differentials. Semantic differentials. So in each object, the individual would run through a more or less large set of these anonym scales, and then choose a position on the scale for each of these. So with that data collected, and this was a massive cross-cultural study, 20 nations up to 30 nations, and what Osgood et al. Did is that they did a factor analysis to retrieve the main dimensions that on which these responses loaded. And their conclusion was that there are three main dimensions that could be characterized as that are universally robust, cross-culturally robust. And these dimensions appeared to refer to whether the object is good or bad, or weak or strong, or passive or active. This is called an EPA, an EPA appraisal space. And of course, there's a natural application to that appraisal space to threat appraisals. Perhaps that accounts for its cross-cultural, the fact that it's robust across different cultures. So we build, in this paper, we build directly on that EPA appraisal space and pose issues, posed objects, which consisted of images of 9 wild animals and 2 nations, Russia and North Korea. And we pose we pose questions to try to get their positions in this 3-dimensional space. Their initial positions, and then group discussion was open, and their final positions. So in this work, what they didn't do, what Osgood and all didn't do, was, they focused on individual responses. So we extend this to say, well, what if you have the individuals are nested in groups? What is the effect of groups in the influence systems of groups on the movements of individuals' initial positions to other positions in the group? So we derived a set of predictions from the influence system mechanism. This is a scalar equation, the influence mechanism, and on object threat appraisals. And these predictions are as follows. Confirmed predictions are as follows. If an initial consensus exists on a dimension of object appraisal, then the mechanism predicts that it will be maintained. Prediction 2, all changes of appraisal are constrained to the min-max interval of the group's initial appraisals on a particular object appraisal dimension. Prediction 3, any change of an individual's appraisal is a movement toward the individual's weighted average of the group's attitudes on each dimension of object appraisal. Thus, certain types of reactive movements are extinguished. Boomerang movements away from the weighted average attractor and leapfrog movements over the weighted average attractor. Those types of phenomena are extinguished. Prediction 4, an appraisal change event will occur on a particular dimension, appraisal dimension, if AII is greater than 0 and WII is less than 1. In general, the magnitude of an appraisal change depends on the self-absorption factor that is implicated in the mechanism. Prediction 5, the mechanism predicts which of 2 types of attitude changes may occur. Now recall that all these were scaled. All of these appraisals were scaled in the -1 interval. A change mechanism predicts which of 2 types of attitude changes may occur. A change that preserves the sign of the attitude, an increase or decrease in the magnitude of the attitude with no change in sign, and a change that flips the sign of the attitude. The mechanism also predicts the conditions under which an initial positive attitude changes to a negative attitude or vice versa. Prediction 6, the mechanism predicts conditions under which particular types of consensus will be generated. The consensus may be a compromise appraisal in the range of initial appraisals that is not any of the group's initial appraisals, or it may be a settlement on one of the group's initial appraisals, minimum, maximum, or other initial appraisal. Final prediction 7, the mechanism predicts a linear correspondence of expected final appraisals with observed final appraisals under the conditions of an influence network topology that is consistent with the convergence of a predicted appraisals to a steady state. This prediction has been validated all along the course of this research program. Its corollary prediction is that the system's derived influence centrality measure, the total relative direct and indirect influence of each individual on the group's settled appraisals, that's also confirmed. Okay. In this paper we present a balance theory. John talked about balance theory, so let me pick up from there. Balance theory deals with the evolution of signed interpersonal appraisals in networks of groups. Its foundations are in the field of social psychology. The current frontier of work on balance theory is the hunt for a dynamical model that predicts the temporal evolution of any such appraisal network to a particular structure in the complete set of balanced networks allowed by the theory. Finding such a model has proved to be a difficult problem. Generalized balance theory relaxes some of the constraints of classic balance theory. The relaxation of formal constraints occurred early in the field of work on structural balance in response to social science fieldwork evidence. It appears that there is only one general constraint, transitivity, and all other realizations of structural balance are special cases. It has always struck me as odd that much of the work on the evolution of networks of signed interpersonal appraisals, the formal work on the evolution of networks of signed interpersonal appraisals, has concentrated on the classic model when the empirical evidence indicated that a generalization was needed. So in this article, we contribute a parsimonious solution to the problem that explicates the conditions under which a network will evolve either to a complete positive network of interpersonal appraisals, that's within the domain of classic balance theory predictions, or to a set of two or more mutually antagonistic cliques. The previous classic balance theory only permits two, at most two. But the empirical evidence indicates there are often more than two mutually antagonistic cliques. And in addition, generalized balance theory, and this model is able to account for, permits an asymmetric structure that allows disagreement, cooperation, and compromise among cliques. These are typically hierarchically organized structures. The term positive contagion in this paper refers to an influence mechanism that generates transitive closures conditional on a time invariant structure of positive appraisals. So in the listed, let me just say this, in our listed empirical work on balance theory, I've highlighted in red its first author, Omid. Omid is a superb PhD student in computer science with whom I've closely worked. He's received an offer from Google and a postdoctoral offer from a Stanford medical-oriented research group. But he loves academia and wants to pursue a research career on problems that he's deeply interested in. Omid is at the top of the heap of all the graduate students I've ever worked with. The in-progress human subject experiment on the evolution of group appraisal networks is one in which Omid's contributions have been crucial. Here, the XO is an n by m matrix of n individuals and m truth statements with truth values on which individuals have heterogeneous certainties of belief in the 0-1 interval. In the standard model, each dimension is assumed to be independent. The introduction of the C matrix relaxes this assumption. In this model, the change of an individual's confidence on one true statement may trigger a change of confidence on another true statement on a different dimension, right? And if this change influences the confidence of another individual on a particular true statement, then that change may also change that individual's confidence on other true statements. And there's a way of, rather, you could take an a priori position on what the C matrix, on the specification of the C matrix, or there's code that allows an estimation of the best fitting C matrix. In many cases, this could just turn out to be an identity matrix if there's no interdependencies among the multiple dimensions. Okay, we've also looked at, this is a paper that I want to bring to your attention. The study of time variant, in all of these studies, it's assumed, it's generally assumed that the W matrix is fixed on a particular dimension, on a particular issue, fixed on a particular issue. The study of a time variant influence network on a single issue is a frontier. The design of human subject experiments that measure such changes requires non-trivial protocols that are best implemented with minimally intrusive online protocols. We've run, all the other experiments are in face-to-face groups. So here I'm talking about online protocols. We've run several online experiments, but note that protocols which require subjects to periodically report their recorded weights and opinions is an exogenous intrusion into the interpersonal influence process, into the interpersonal process of the group's discussion of an issue. Ideally, the data should be obtained with unobtrusive monitoring methods from which measures of groups, networks, and opinions are extracted. Such experiments may involve data collection on text messages or video conversations or other metrics such as eye movements, facial expressions, body gestures, voice strengths, participation rates, interruptions, and so forth. There is a long-standing field of work on conversation analysis. I'll never forget listening to a talk given by a colleague in my department who spent an hour talking about a 17-second video recorded conversation. I walked out of that room and thinking how large the jump to an influence network is. Perhaps it's not a large jump. Don't have the answer to that question. Recently, I'm closing with this. Recently, we've run human subject experiments based on remote online interactions among human subjects. The lesson learned on the deployment of online protocols is that 2 dedicated on-site technicians are important to pursue a research agenda that involves human subject experiments on influence systems. 1 to quickly modify the code and 1 to administer the experiments. Without such, we find that the pace of work is substantially diminished on executing a series of non-trivial protocols. Finally, let me point out that designing protocols on human subjects and getting them approved presents its own challenges. Stanley Milgram and Solomon Asch were the classic masters of the craft involved, especially in regard to designing variations on a single baseline protocol. So that's my talk, and I want to say that I've listened to every lecture that has been presented here, and it's been a really interesting last couple of days. So thank you.
Thanks, Noah, and thank you for very interesting talk with many exciting results. I think now we can open the floor for questions. If anyone has any question, please feel free to unmute yourself and ask. Yeah, maybe I can start with the first question. It's a very high-level question. So Naomi talk about nonlinear models like in her talk. So if I understand correctly, most your model are linear models. So I was just curious, like, in what scenarios it's sufficient to use linear models, and in what scenarios maybe we have to look at non-linear model. In particular, at the beginning of the talk, you talk about like there's a risk shift and also polarization. Is possible to explain like polarization because there's some non-linearity in the system? Is that possible?
Well, it's possible to by polarization, you mean a group that eventuates in, let's say, a bimodal or trimodal distribution.
Right, right.
And actually, you can get that from a linear model. That paper was published in Control Systems magazine, 2015. That paper was delivered, I did that paper to engage the control systems community. And I took that problem as the focus of my attention. So it doesn't require nonlinearity. The issue of continuous, it blends. It depends on how you define the length of the period. And you could just go, John, what he showed on the model, his the cost minimization process. In that context, you can get situations in which moving to a continuous time model is really useful. Mm-hmm. I like linear models because they're simple, and they have this intimate linkage with the literature on graphs and graph theory. And so there's just this such a natural intimate relationship between the type of linear models that I've been dealing with and graph theory theorems that I really like, and so I've never myself found the need for going into a continuous time model, but that's my preference. So,
sure. Thanks a lot. Yeah. Any other questions from the audience?
I guess if I could ask a question, that was a very interesting talk. Thanks very much for sharing all these. There's this sort of question at the kind of boundary between modeling and then some of the changing way that applications are changing. If I think about the sort of online domain where people might increasingly be deploying AI tools to help them filter the information that they're getting or to aggregate the information that they're getting, do you think there are interesting opportunities there for sort of adapting any of the models to how the agents, the individual people at the nodes might be sort of processing the information that comes in, possibly even using some AI layer that they're not sort of completely explicitly watching?
Okay, so that's what Francesco and Ambuj and I are thinking a lot about these days, and we're thinking about it in a way that would allow experiments to be conducted on it. And the various, particularly interested in a differentiation of the types of roles that AI agents can play in the context of a human group that's considering an issue, right? There are distinct, you could define a set of distinct roles in which they are just information resource, or they're actually monitoring sort of the performance, the relative expertise of the individuals, and then they're sort of supervising it, but not intruding into the mechanism. So what's interesting about it, so trying to study the various modalities in which AI agents could contribute to an improvement of the performance of a human group that's deliberating on an issue is really, is really a fascinating area. Did I answer? Am I addressing your question?
Yeah. Absolutely. Yeah, that's a very interesting point, and especially about the different roles they could play. Thanks.
I'm thinking of, in particular, you remember the Delphi experiments that were run by Rand? There was this whole sequence of Delphi experiments, and they set up this system. They set up this system in which there was a procedure to follow that anonymized the, they weren't talking directly. They were just reporting their thing. The idea was to avoid biases and to get more rational decisions. Well, you can imagine a sort of a Delphi setup in which AI agents are folded in different ways to kind of steer the group, contribute to the group's growth of collective intelligence. So it's a really interesting field that's now developing on that kind of, in that domain, right?
Yeah, absolutely. Thanks.
Okay, well, again, thank you very much for your attention.
Thank you. Let's thanks Noah again, and let's have a virtual clap. Given the interest of time, I think we will end the second talk here in about like 30 minutes. We have the third talk, also the last talk of the workshop, given by Weina Wang from CMU. So hope to see everyone in half hour. Okay, thanks everyone.